Hi everyone, and I have to say, Chris gave a fantastic presentation that give us the understanding of knowing intelligence and doing and predicting intelligence. That's so fundamental about the I think the AI foundation model. So I'm grateful Chris just start and give a detail of this. And I will, on behalf of our team, to present how we, as Shanghai Research AI Institute, we built a foundation model, and also we will share what we have finding and what some of the innovation that along the way that we build this FoxBrain. Sure. Okay. So first, I think I will give a quick glance of Foxconn about strategic platform. So for Foxconn, we have 3 strategic platform. Sorry. Should go this way. Okay. So we have a smart manufacturer platform, smart city, and smart EV platforms, which is 3 critical platform developed from Foxconn. And for us as a foundation model team, how we built this FoxBrain foundation model that's supporting the development of these 3 strategic platforms. So from manufacturer to smart EV to smart city. So in which of these platform carries a various application and need the AI foundation model to help to make the decision or a data-driven analysis, and also many other applications we need to have the foundation model to handle. And here is entire stack of building an application with the AI foundation. So we have the bottom part, which is the AI factory infrastructure. And on top of that, we will have the AI training and inference framework. And after these 2 first layer will help to produce the foundation model. And this foundation model continue to need to have the application at the top to help to make this model to the hand of the user. Yeah. So we will share with you our the development roadmap that we aim for. So from the you can see from the first generation, we focus on building the language foundation model, and then we continue to expand to the multi-model that the model can handle other modality, can handle speech, vision, and other modality that expand the capability of the model. And then we continue to make the model need to, like Chris mentioned, need to do predicting intelligence. So which basically we aim for the model can understand the dynamic of the world and knowing planning and reasoning. And the last foundation model we aim for, which is we try to bring this model to a certain application that Chris mentioned. It should be 20% of a good enough model to be used, and we don't aim for something like general intelligence. We just make sure that work and help the company strategic platform can drive their work. Yep. So I think I just share a bit about the 3 platform and also our roadmap development of FoxBrain. But before we jump right in, I have a quick recap of recent development and a bit inside of this foundation model. So let's jump right in. So I think we all raised the attention of foundation, especially the language model or generative AI since I think last 2022, I think, yeah. And after that, the rival of the foundation model continued to grow. So we see like from Europe, we have like Mistral, and from China, we have Alibaba or DeepSeek or many other big tech companies from China. They still continue to build a foundation model. And from the US, we have the open source driven foundation model, which is NVIDIA and Meta. From proprietary, we have OpenAI ChatGPT Siri, GPT, and Google, we have Gemini Siri. Anthropic, we have Claude, and XAI, we have Grok Siri. So this foundation model, to give you a sense of how good of this model. So on the left figure, which is the showing the various human tasks, and now these models are basically on par or even outperform these human tasks, various domain from vision to speech to natural language understanding. And on the right figure, which is one of the benchmark that show the IQ, basically to test how intelligent of this model. But if we look at this latest generation of this foundation model, which is already surpassed like average IQ 100. So basically, it show this foundation model is like growing and also significant like improvement over time. And it's might reaching to the point that it's saturated, but we're not sure when. But it's right now it's showing the model continue to improve. Yeah. And look inside of this model, I have the one graph to show here the x-axis, which is the development over time of the foundation model. The y-axis, which is one factor of scaling, which is the number of parameters of this foundation model. And we can see the latest generation model, which is around a trillion upper foundation model. And the same scale with this parameter, which is the training. So the compute to train this model is also scaling significant with the size from the 100 million petaflop to a billion per petaflop. And here's some typical also one scaling of the data engine to train this foundation model. So it's now you can easy to see the model that trained from 10 trillion to 100 trillion token of the training data. So this is a massive amount of training data to train the knowing intelligence, like Chris mentioned. Yeah. And yep, that's just a quick recap and also knowing a current state of foundation model. So I will jump right in how we FoxBrain built. And we have three, before we start, I think our team just roughly around 5 members. And we don't have a data label team or data building team. We just engineering everything by the AI model. So we have 3 important blocks that in our foundation model. One is how we build the high quality data engine at scale with cost efficient. The second is how we train this model with the across different clusters efficiently. We have usually when we train the model, we will have the time constraint. So we only have 1 month of usage of the cluster. How can we finish all the training in 1 month? And the last piece is how we develop the cycle to improve the model, knowing how many version and also what kind of the task or domain we need to focus in able to finish and improve our model over time. And I try to share the some just critical important block and how it's linked together. So the first one is starting with the data block. So how we build synthetic data, domain-specific data, which is smart manufacturing or EV and also city. That's how where we focus. And we also try to gather open source or public data available. And starting from data, we will try to build a model. So, but from this, we just aware, okay, how can we leverage available open source or existing foundation model to help us to continue to build on it? And how we train the model, we have to check whether there's a suitable algorithm with these matching with our need and also latest development of the foundation model. And we have the AI factory help us to train this model. And last, how we decide the iterative improvement, which is a cycle to help us diagnose what the limit and what the domain we need to focus to continue to make the model better. So first we look at on the knowledge of the how we build a knowledge to FoxBrain. So in this we focus on certain category. So we try to make sure our training data that can include wide range of knowledge to enable to make the model learn better. And some kind of knowledge we need to focus than the other. For example, like internal community use, so we need to expand the knowledge of the model on this. And some other domains, so we need to focus and knowing what we input to the model to train the model. Another part of the knowledge, we focus on the multimodal knowledge. So in this, we focus on manufacturing data. The second part, we focus on autonomous driving. And last, we focus on robotics that help us to build the practical and useful foundation model that helps the 3 strategic platforms to develop. So, with the data I just showed, we have no member to do a data, and we don't hire anyone to do a data labeling. So how can we handle this? So this is in the age of AI, manufacturing AI. This is the title I wanted to show. But just imagine we have available this foundation model, whether it's open source or proprietary. How we leverage this to build first the data curation, quality management. The second is data augmentation enhancement, the synthetic data generation, and domain-specific and agentic agent data pipeline, and also multimodal data generation and integration. So this is what we are focused, how we leverage the current generation of the foundation model help us to do these tasks. So that's why we have no labeling data team to help us to build a large-scale data. So I will give you a typical pipeline of the language data engine. So in this, I want you to focus on the last 2 pieces, which is the data quality control and also data enhancement. If you look at the bottom, which is the model foundation base, so we're just using this model help us to do these tasks instead of we human just look at this training sample whether it's good or whether it's not. So we can't handle this because the scale is massive. So we need to leverage this foundation model to help us to do this task. The second, which is the multi-vision language data engine. And again, so we can see in this entire data engine is multiple building block, which is just a foundation model base to handle these tasks, from quality control to captioning generation to domain classification, even to enhancement. And another pipeline, which is building for a physical AI foundation model. Also the same, we have a bunch of foundation model that help us to do from the, okay, so from the, you can see from the task, generate the instruction, to the generate a video trajectory or some other that action we need to train the physical AI model, and to evaluation this generation. So we are just using a foundation model base to help it to just automatically help it build the data and generate at scale. So I just mentioned a lot, but I don't give you a bit of detail. So I try to bring some detail here about like quality control and also data enhancement, how we're doing this kind of task. So first, let's assume we have a large training text corpus. How can we use this model, help us to process, enhance this? So which first is the quality control. So how can we define a set of criteria that just teaching the model, okay, look at this training sample, please help me read my criteria and check whether this training sample is passing a quality or not. So I have one example here. So we have a paragraph which is well written, nothing wrong with it, right? But in our design, we have a set of criteria, and this criteria we define is as a quality training sample. So after we define this well and finish, we just let the foundation model itself to reading the training sample and checking with our quality critical, and then this training sample is just not passing our score as 3 as a quality. So it's just 2. So basically this training sample as a low quality for us. But for a normal foundation model with this filter, it might be just easy pass. And now I give you another example of how we do data enhancement. You have a raw data, but not good enough. You might need to enhance it better, right? So in this case, we design the one we call co-star. What does co-star mean? Which is context, objective, style, tone, audience, and response. I give you another easy to understand this. So if you look at the, Chris mentioned the entropy information. So how you make the model generate a wide range of, or diversity of entropy, right? So let's think of human. So how can we steering this model? So we based on the concept of education, occupation, or your background, a lot of different things. So like from culture, from different country, different region have different things. So how we incorporate this information to guiding the model to generate more information, but not a lot of bias inside. So we try to cover this wide range. Okay, I'll give you an example. We have this bar graph, which is just a technology. So how can you turn this bar graph to, let's say, high school student in our example here. So in high school student, the student might not have a lot of background knowledge about technology. So with this case, we design the objective that handle for a low level or the student that just beginning to learning something. So in this way, if we guiding this to a current foundation model, help us to steering our data, then it will generate a new form of context information expressing that helping us to generate more variant of the data, but without like the same information that the same original one. And to continue, I have one figure to raise here is about right now. I think a lot of us using generative AI model to do daily tasks. For me, I'm using it to write email. Even when I send the message to Dr. Lee, I also using AI to help him to refine whether it's good message. So I think more and more the next generation of model will be trained on the synthetic data, because a lot of content right now on the internet which is generated by AI, right? But is that good? I think it's good for building a foundation model perspective. So let's just ignore the caption, it's a bit too long. I try to give you the first figure. If you look at the x-axis, it's about the size of the foundation model. The y-axis is performance or the accuracy in some benchmark. And the right figure, which is x-axis, is the number of amount of training token you train the model. And the y-axis is also the accuracy. So if you look at the model side that train on synthetic data, the model learning and converging faster than the raw data or the human written data. And the performance of this model also significant improvement, which is try to show that synthetic data might help to more efficient to train the knowing intelligence, right? And help us to reduce the cost and the development of this foundation model. And for us, we also leverage the synthetic data pipeline, but we focus on the agent. So why we need this? Let's imagine you have the domain of mathematics and programming language, which is require the expert knowledge to build this data. How can you build that? It's require verify the check quality of the answer, whether it's correct or not, right? So we try to build this kind of like synthetic agent data that generate the data for complex problem like math or programming. And another part that for physical AI that we focus also on the synthetic data, on the text to video and video to video, image to video, text image to video that generate more that about unseen or some critical environment that we want to have. So I give you one example that we have the input of the image and the text. How can we just generate the entire next video that help us to build the robotic application, right? And yeah, that's just how we just leverage a foundation model to help us to build the data engine at scale. So with just no label team in our research, and yeah, we luckily, we continue to scale this data engine massive across a wide range of tasks and domain. Yeah. And just finished that the first part. And the second part is when you have a data, how you train the model. So I try to share how we scalable, efficient, train the foundation model. So let me quickly here. Usually training a foundation model is a multiple stage. But I try to make it simple. We have two stages of training. One is you pre-training the model. You have vast amount of knowledge. You try to compress this knowledge to the foundation model parameter. You have to compress this information, right? In the second stage, you try to teaching the model that follow a certain instruction or some preference alignment that you want the model to have. And also you try to teaching the model to reasoning through a problem that need to think before it's answered, right? And to training a foundation model, this is a lot of requirement, but I want to focus on this section is how we distribute the training of foundation model. So I give you one example of a series of foundation model developed by Meta. We have, which is a transformer-based model, is a stack of attention block. You stack much more of attention block, the model will get deeper and the size will get bigger. That's why you see from 8 billion to 405 billion per model parameter. And if you look at this figure, the x-axis is context information. You can think the context, which is the working memory of the model. On the y-axis is the hardware memory need to hold this context information. So if you think a current generation of hardware, we might not have a single GPU that have a 1.5 terabyte of memory. It's just like not available, and the hardware will not meet to hold this model. And that turns into how you shard and distribute the model across different machines and train it effectively. So there's some basic and some advanced parallelism to train this model. I just show it here several, but it still have some more. So we have like a data parallelism, which is you just split the data at different patch, and then you feeding this each patch to train the model. A tensor parallel, which is the idea you have a model layer, you just cut it as half of this on the one GPU, another half on another GPU. A model parallel is the same. You have several layers. You just split the model into two chunks of layer, right? So one chunk of layer in one GPU, another chunk in another GPU. And then another one is a pilot parallelism, which is more about like how you feed forward and back forward the data. And so I try to give you some about the statistic when you leverage this parallelism in terms of the memory footprint, because like I mentioned, we might not have enough, the machine that enough memory to hold this model. So that's why when we combine a different parallelism, on the first figure, which is the one with x-axis with the context information we need to model to have, but with one model that have a 65,000 context length, we might need like roughly more than 2.5 thousand terabyte memory. So we don't have enough the memory from a single GPU to doing this. But if we combine a parallelism, we can just compress this model about a memory footprint and across this to a different GPU to help us to handle to train the model. And there's one headache. Even we define the parallelism success, but there's one problem. It's a problem about how you set it right. You have to find a sweet spot in your training. So what I mean is, it depends on the cluster, the accelerator, type of the accelerator you have. You have GPU, TPU, or other kind of the training hardware. So how you have this type of hardware, how the communication between each is a crucial problem. So I give you an example. From this point, I use setting parallelism from tensor parallel to parallel parallel. But if I use another setting with the tensor, I think I just passed slide, sorry. So, okay, if I use another setting like a tensor parallel, a 16 parallel, so what we have to pay? We pay the cost of utilization. We not utilize it well. If I utilize the cluster well, I just need 18 days to finish the training. But if I'm dumb, I just need to spend 118 days to finish the training process. So that is the part I mentioned. We need to find a sweet spot to optimize the cluster to train it effectively, to make sure we utilize the high usage of our training cluster. And I think I will give you a bit insight of the training look like. So when you first is a pre-training. So pre-training, like I mentioned, we usually train it at a very large scale. As of stage 1 is 1 trillion of token, so it's a massive data. And then if you leverage the base foundation model, you don't need to do this stage, but you need to do a continued pre-training. You append the new knowledge to the model, right? So appending new knowledge, usually you don't need to have a lot of data, but you need a high quality from 1 million to 1 billion scale data, right? And this just from pre-training, the idea of next token prediction is which is mean when you train the model to predict next token, when the model predict is right, the training loss behavior it seems to be right. It will get lower over time. But if your training might not setting right or the data something wrong, you can see the model will get a situation that unstable training. Unstable training, which is the model behavior just weird and just going up and down is uncontrolled during the training process. And usually if you have the unstable training, the model will not learning effectively at the end. And another one, I will try to give a glance into the boat training, which is the big stage. Within this big stage, we'll have multiple of training stage. Let me give you an example. So this diagram looking like really hard to understand, but just bear with me. So we have around like 8 stages, but we just focus on some here. So like the NVIDIA Nemotron, when they train the model, they divide it to like curriculum learning, right? So you see the stage 4 and stage 5, they try to teaching the model to learn some certain category or certain domain of data, like we see math, coding, something, to try to teaching the model to learn some knowledge. And then they continue to train with the reinforcement learning to teaching the model to think better or to handle complicated tasks. Another example from very popular model is DeepSeek. So they also have several stages of training from instruction fine-tuning, teaching the model to follow a certain task, until reasoning, that teaching the model to think through a problem. And for us, FoxBrain, what we need and we approach a bit different, which is the dynamic boat training. What I mean the dynamic boat training, you can see here first, we try to diagnose what the model limit and what the model not good at with our certain evaluation or stage of design to diagnose the model. And from this, we can just diagnose what it limit, and then we improve the data itself, and then we train the model and continue to improve the model until it satisfies what we need. And then we just have a good enough model that Chris mentioned, that's useful, and just help us to build the application on this model. And usually training or both training the model, we might just need to find also where we need to stop. We cannot just training the model over and over or repeatedly on our data itself. So we need to find like what the right step we need to stop the model, which is we find the best checkpoint of model during the training process. And then you stop and ship the model to the application team. And yeah, that's what I just show about the training process. It's a bit abstract, but it's a lot of engineer in the background when you try to train the foundation model at scale. And last piece, we just have a benchmark evaluation. One part is how we build the benchmark to know how good of our model is and how bad of our model in some certain tasks of benchmark. So the first type of benchmark, which is you have the metric to understand the model, which is you look at the number, the higher is the better, which is some standard benchmark like MMLU, or right now is a lot of benchmark. I am not mentioned here is like 100 of different kind of benchmark to test the model. And for us, we built the first generation language model. We focus on also a lot of different benchmarks, but for us, we focus on the Taiwan MMU, which cover like 66 category from the easy to professional type of the category question. So to show the effective our training and also the optimization of our data engine, we have the FoxBrain's model that's based on Meta Llama. And we can see it's cover a wide range of tasks after training process, pre-training and post-training. The model seems to be improved better across different tasks and benchmark. And here's just another, yeah. And the second type benchmark I think is about like how we evaluate model on a kind of question that don't have ground truth. So let me give you an example of that one type of this question. Can you describe the moon to the 5 years old? So from my way, I can just talk to a kid in a different. From Dr. Lee, he might just explain to his kids. It's differently, right? So this kind, what in my description or my explanation might not wrong, and Dr. Lee might not wrong also. But how can we evaluate this kind of question? How kind of benchmark? So usually they will build like a common approach is you will have a lot of answer from different model, right? And then whether you can have a human just grading different criteria, you can set like 10 different criteria to evaluate my answer and Dr. Lee's answer. So in this case, we can just evaluate on this by human approach, or you can just using a model itself to help you to judge or to evaluate this response from the model. So one kind of benchmark related to this, which is Taiwan MT bench, which cover from coding, humanities, writing, STEAM, role-playing. So these kind of benchmark, they might not have a certain answer, so it can be multiple answer can be right. So in this case, we can just using the foundation model itself as a judge to help us to reading through, evaluate through criteria and how well these criteria and sum up give us score, right? So I just show how we benchmark from the standard to a human eval or some LM as a judge to evaluation the model itself. And now when we have the model, we need to just using this model for our application. So for us, we're using an application for office workload like the rack. I think it's very common right now. So in this rack system, I show you one example. So for us, we're building the rack to help us to do research better, to reading a paper, summarize a document. So for example, here we have the technical research paper, how when we understand it better through using a application. So for example, here we have the model going through, reading through the entire paper and give us the good summarize. And so at the end, this model will also try to describe in the way that for us too easy to understand. So I think, 1 minute. Just here we can just like have the model help us to drawing the map, mind map to help us to easy go through the document. So this is very kind of useful application when we have the foundation model to help us to do research. And another one I mentioned is about agent development. So this agent will have us. One example, we built the code agent to help us to write a better programming. So in this, we have the coding agent, which is defining with a different block from the planning, code, and testing, and also evaluate how well this programming. And yeah, I think that's it. Thank you so much for staying with me until the end. It's a bit boring regarding to technical. So thank you, everyone. So I'm happy to take any question.
Is there any questions?
So you mentioned synthetic data.
Yes.
Right. But synthetic data has a danger that it can bias you out of the real world distribution by, however you're creating
Yep.
it. what do you think is the right balance between synthetic data and real data that will lead you to a model that is reasonable?
Yes. Thank you, Chris. That point out is one of the critical issue when we building the synthetic data. Is one of phenomena we might not aware is entropy collapsing, right? So when we generate the synthetic data, we might not to just think like, okay, I can generate as much as I can. I can generate anything as I can and train the model on this. I will get a better model. The answer is no. You have to be super careful when you generate synthetic data. And one thing Chris mentioned that how we see the danger. So usually we carefully try to knowing how much of synthetic data and how different category of synthetic data we put in to train the model. So we're careful to select the category and then combine them together. And from some complicated tasks like mathematics or coding something, we will need to verify, check whether the answer is just like verifiable or answer in the right way. And then we can append this to the training. Usually there's one word I want to say is we generate a lot and we throw in a lot and pick it a bit. So yeah, some that we just spending a lot of compute to just synthetic generate from a model itself, but a lot of them we need to throw away. And we just pick up some of them that just passing some evaluation and also some of the kind of like the tasks and domain that we care. And that's crucial important, yeah. Thank you, Chris. That's a very great question. Yes.
Of getting real data from the Foxconn factories,
Yes.
and including some failure and accidents, and these are very valuable. No?
Yes. So thank you, Professor Zhang, for raising this. So when we build the FoxBrain, the final purpose, we don't really build a ChatGPT version of the foundation model. What we build is we try to focus on 3 strategic platforms, what they need, and what kind of application we need to focus. Then turn back to the Professor Zhang's question that we focus on smart manufacturing. To be able to build a smart manufacturing foundation model, we need to understand what kind of the tasks in the manufacturer, especially Foxconn is a company regarding to manufacture. So we can gather a lot of factory data from different plants of the country. And from this, we can just teaching the model itself so they can understand kind of like the component, the content of the video and other things that later the application team, they were using some tasks that related to these input, then the model already learning through process of retraining. So that's the purpose. We adding a lot of manufacturer data within the training process and in the next stage of our development multi-model. Yes.
I think Rick should put some more practical examples that our FastBrain is used in the factory Q&A system, right?
Yes.
So actually, we have some real use case, and you don't put it.
Sorry.
Yeah, but I really like the paper reading application, so please make it.
Okay.
Always, okay. All right, any other questions? If not, then we will take a 10 minutes break. Okay, so please come back to the room at 2:30, and we will continue our next session. Thank you.